there was some problem. So we are going to repeat that because I am in the full screen mode. I could not get proper feedback as to what is going on. And there was a problem in between for a short while last class, but then I resumed. But then I think I was only speaking. Okay. So we are going to repeat the last class. So we told that our main topic of study is strap-down inertial navigation. This is the modern method of inertial navigation. Strap-down means tying the sensors onto the body or vehicle along the desired axis so that the measurement is done in those body axis. Even before the strap-down systems had come, the earlier version was called stabilized platform inertial navigation. What is this stabilized? We just briefly look into, just see that, know that such a system is there, was there, and later it was got rid of. And then what is it? We are not going into the details of that, but it's quite simple. The main difference is in strap-down inertial navigation, you need to do a lot of computation. So you need powerful processors, calculations. So in the strap-down stabilized platform inertial navigation, the computation is very much reduced. That's why in the earlier days, when the processing capability was less, and this was the preferred one. Not the theory was there even then. So you just see what is that. So this is a gimbal, and the outermost ring is called the outer gimbal, which has got a freedom of motion about this particular axis. See, I have shown the line. The gimbal points are here and here. And you have a middle gimbal like this, and that gimbal axis is in this way, as shown as Y, and the gimbal points are here and here. And inside to this gimbal, you have another platform. Again, that is gimbaled onto this point and the bottom of this ring, this axis, and that is the Z axis. Now, the rotational freedom wise, the outer gimbal will have rotational freedom about this particular axis only. And this middle gimbal will have rotational freedom about this Y axis only. And this inner gimbal or inner platform has got rotational freedom about this axis, Z axis only. And now, if you see, look at carefully, earlier in one of the class, we were talking about angular motion simulator having an outer gimbal, middle gimbal, and inner gimbal. This is exactly the same. Whatever angular motion coming onto this is, we call their specific angular name sequence, theta about x-axis, psi about y-axis, and pi about z-axis. So the angular rotations here about the outer, middle, and the inner, those three angles are actually the Euler angles. Now the idea is here, ideally these hinge points, gimbal hinge points, are ideally having zero friction. Here, and here and here and here and here, the friction is 0. If that is the case, what happens when you put this entire system onto a vehicle, fix it, the fixing is, that is what is shown with a different color here, the black color, that the whole thing you take it by 2 hands and fix it onto a vehicle, aligning these axes as you desire to align with the vehicle axis. Then, once you start with the particular orientation of this platform, and then the angular motions of the vehicle come about to these fixed points, since there is no friction here, here, no angular motion will be transformed or transmitted to the platform here. That means whichever orientation this platform was initially held, it would remain in that direction. And for example, if you are talking about an inertial frame to which these directions X, Y, Z are initially before navigation start is fixed onto the inertial frame direction, then even after the vehicle taking off and then doing all sort of angular motion, that will not be transmitted to the platform, and the platform still will be oriented towards that initial Xi, Yi, Zi inertial frame. And that being so, see, there are 3 accelerometers here aligned across 3 axes, and they are now oriented towards the inertial Xi, Yi, Zi axis. And the outputs of these accelerometers are directly in that inertial frame. And if you want to do the navigation, you have to simply integrate these individually to get the velocity in the inertial direction, the 3 directions, and then further integrate to get the position in those directions. Then the question may come, there are something sitting here. What is this? And this is nothing but the gyroscopes. And see here also the axes are aligned. One axis is along X, another is along Y, another is, it's not properly shown in this figure, and they are like that. And then the argument was no angular motion will be transmitted inside. Then why? So that means there is no angular motion to the platform. Then why do you require this gyroscope here? That is the natural question. And the answer is, even though we said the friction of the hinge points are ideally 0, practically we cannot achieve this 0 friction of these gimbal points. It's impossible. We can minimize to the greatest extent possible with the mechanical engineering technology level, but never you can make it 0. That means when the vehicle undergoes, because these 2 points are fixed onto the vehicle undergoes angular motion. Because of some small finite friction value here, some amount of angular motion will be transmitted to inside. Am I audible? Is it going on okay? Hello?
Yes, sir. Yes, sir. It's audible.
Yeah, I will ask your feedback now and then. Now, we said that some small value of angular motion is transmitted here because of the finite friction of these hinge points, and that angular motion will change, disturb the desired inertial orientation in which this platform is supposed to be, will be now altered by this small angular motion which is transmitted to this platform inside. And that being so, that need to be corrected. And in order to correct, we must know how much angular motion has come there. To measure that, we put gyroscopes here, and these will measure the residual angular motion which has come here, and then drive the three gimbals, those drive electronics and drive systems, gimbal drive, nothing is shown here. This is only symbolic diagram. Drive these gimbals using this measurement and keep still the platform in the inertial direction, desired inertial direction. So one important point the students have to know is that compared to a strap-down system, here the range of the angular rate which is to be measured by these gyros will be very small, because of course there is an attenuation of the angular motion from outside to inside. Therefore, the range of this is required to be small, and also usually the bandwidth or also the speed at which, because some dampening happens over these hinges, and because of the dampening, the bandwidth of the angular motion is also reduced, and by which the bandwidth required for this angular rate measurement at this platform is also small compared to a strap-down inertial system, wherein these sensors are strapped or tied down to the body axis itself. So this is a simpler system which was existing in till the early or late 60s. Strap-down system was there. Even, the Apollo 11 has used this system. And early 70s is onwards, because the computational power of integrated circuits, microprocessors have gone up significantly by that time. So the entire technology, the whole problem is the strap-down is, you have to machining, mechanical, this one, and suppose a repair comes. The entire assembly need to be opened. The entire assembly need to be opened. And then in the opening process itself, these hinges will get some affected. And then you have to reassemble the entire thing. To reach the sensors, you have to reassemble the entire thing. The whole thing is housed in a special shaped shell. And that is an enormous tiresome process, and therefore people preferred this strap-down system compared to stabilized system, and then the required computational power was achieved by processors by the time, early 70s. So here onwards, our focus will be on to the strap-down inertial navigation system. So we set that background a little bit, maybe some sort of a repetition. It doesn't matter, because this lecture is getting recorded, and therefore those who are going to listen later, they should be in some kind of a full start to end. In that sense, this is important to repeat. So let us take an accelerometer like this. It's a really symbolic accelerometer. We're having a hinged pendulum here, and then subject it to free fall under gravitation. then what happens? This case we discussed earlier, but we will repeat again. This pendulum or the hinge, the case, everything is subjected to the same amount of gravitation. Just imagine that the difference, there will be a small difference in the gravity here, gravitation here and gravitation here to this because of the distance, because gravitation changes with distance, because you know that there is a gravitation gradient. So we are assuming here the gravitation gradient is 0. Our small systems is like that only. This value of gradient is very, very small. So there is no relative motion of this pendulum with respect to the case when the free fall is happening. The case and the pendulum as originally it was, it will remain the same. Now, it will, even though it looks simple here like this is a point of understanding to talk about an accelerated frame, how do you feel and all that. So the point here is the pendulum do not have relative motion with respect to the case, and therefore its output will be 0. What effectively it means is it cannot measure this gravitation under which this fellow is getting accelerated. That is the point. Now, there are in physics ways of telling this in a different way and all that. I think engineering point of view that right now it's not required. Okay. I think you understood this. Now you look at, suppose instead of assume that a person like me have the capability to measure the acceleration. I become the accelerometer. And then I become the accelerometer. I am put under a free fall. I will feel something, isn't it? That feeling something is different from what I feel now while sitting on a chair while presenting to you. While sitting on the chair here, I am constrained to move down. I am held by the chair, fixed platform, and I feel my weight here now. The same myself as an accelerometer, when it's freely falling, I will not feel this weight. And this, what we are talking, is exactly the same. Another way of telling is that when a body is falling down under gravitation, the free fall is due to this gravitation. So there is a gravitation acceleration downward. And when a body moves, accelerates in one particular direction, always and always and always, there will be an equal and opposite inertia force. And these two cancel in effect. That is why the person doesn't feel his weight and it feels his weight as 0, weightlessness. Of course, we are neglecting the air friction, damping, other things. Okay? Ideal case in vacuum fall. Fine. Now, so this is now convention. So this, if the pendulum moves down, suppose now suppose this accelerometer is accelerating upwards like this, then the pendulum will move down. We know this. Somebody is sitting on a bus seat. When the driver accelerates the vehicle and he gets pushed backward, and then he puts the brake and he gets a push forward. And this is exactly same. That is due to the inertia force. And so if the acceleration coming in this direction is the real motion of the pendulum is going to be downward. So we need to put a sense of direction for our purpose of mechanizing measurement need to be say that whether my output is positive or negative or zero. So therefore, I will say that I will mechanize if the pendulum moves down in this direction, I will take my positive acceleration is in this direction. That is by convention. So this is already we have seen in the previous slide, this cannot measure the gravitation. And so therefore this acceleration is that measurable inertia force, otherwise called specific force, other than the gravitational acceleration. So here two things we have done. One is setting the sense of the sign positive, negative, and the convention, as well as introducing measurable inertia force called by another name. Usually this is the popular name, specific force. Of course, gravitation we know, this gravitation law, this is a gravitation constant here. Free fall we explained, and this is a well. But one thing you should remember, the gravitation is a function of position. If you know your position vector, and then you can, with the proper models, you can get that vector by calculation. Okay, we'll go next. Now, let us take a launch vehicle and use body, this axis or the body axis of the launch vehicle. Am I audible and then things are going on better?
Yes, sir.
Now, in this vehicle, suppose I put the accelerometer as it is here. This is called the equipment bay region. There are many accelerometers. One I am showing, I am putting here. And the vehicle is accelerating upwards along the Z direction. Upwards along the Z direction. Then the accelerometer sitting here, the pendulum will move down. So that means this motion of pendulum down, I should call it plus Z acceleration. Okay? Yeah, this is very straightforward. The previous slide also we explained this. Again, repeating, these things are important. Now, this is a case where when the vehicle is accelerating up vertically up. Now, assume in the ground when the vehicle before taking off, before lifting off and accelerating upwards, it is stationary, vertical. At that time, it is in a static vertical state. At that time, what will happen to the pendulum? Naturally, the pendulum will move down. Why? Because this is sitting in like I am sitting in the chair. This is the whole thing is sitting in a elevated chair called inside this room. Actually, the whole unit wants to move down under the action of this small g. I will tell you what this small g is. So it really wants to go down, but you are restricting it, and therefore it will measure. It is a constrained situation. It will feel its weight, and therefore this pendulum will move down. Therefore, the static state, pendulum will move down. So in our mechanization, we don't know whether we are static or we are moving, and all those things we cannot distinguish it. So whatever we mechanize should be a uniform mechanization which would take care of any condition. So here we know that pendulum moves down and you will going to get an output, but I should interpret that output as opposite sign of this. That is what, here this direction is negative Z direction. Our measurement, we told that positive Z direction. Here also, let's say negative Z direction, and this is positive Z direction. And because this is called GI, this is the actual GI, and this is called its opposite sign. What is this GI here? The next slide we will see again. This is actually the gravity vector. gravity vector and this gravitation are slightly different. In the high school, we used to study, but here this is very important. That small difference will make a whole lot of things different. And this gravity vector is downward in a particular location. Downward means, yeah, local down. And this we say by measurement in the opposite direction. Okay. So the sensor is constrained to move by convention without way upward acceleration. Correct. Okay. So this is set right. Now let us again distinguish this gravity and gravitation for better clarity. And there is an object here sitting at this point. And you draw a line towards the center and without this vector, and that is the gravitation, capital G, gravitation constant into m1 and m2 by r square, that one. That is this vector. Then because Earth itself is going around its own axis with approximately 15 degree per hour, this point actually is, there is a centrifugal force because of that rotation. That centrifugal acceleration is this particular vector, this small vector. Somewhere around in the static condition for our location, it will come something like 300 micro G, like of that order, 200, 250 to 300 or something like that. You can calculate actually. Omega, the radius, our latitude we know, therefore the radius here we know. So it can be easily computed in a very simple way. And this vector is outward. And the vector sum of the gravitation and this centrifugal, the resultant is this red line. And why this is drawn is, I have completed a parallelogram here, like this, to get this equivalent gravity vector red line, and calling it Gi. Of course, I is just a matter of preference, maybe for the inertial frame. It could be any other frame also. But physically, this is a vector. The vector sum of these two, centrifugal as well as the gravitation. And that is gravity. And if you know this, and you call only this, and that is gravitation. Okay? That's it. That's a difference. So the vector sum of these two, no, this is different. Okay, I'll come back. Now let's say, suppose the vehicle has not lifted up, it is in the launch pad and sitting there for maybe several days, few days before actually the launch starts. And before that, the system is cooled, several tests are done, and so on. In all those situations, the system is in the static condition like this. This is equivalent to saying that we are putting the system here. Of course, the height is not shown, or the large vehicle height is nothing compared to the radius of the Earth, and therefore that can be ignored for the time being. And you are at this point, your large vehicle is at this point, and you are testing what really happens, and we are navigating an inertial frame, Earth-centered inertial frame. And because you are in the static condition, and still you want to evaluate your system outputs by way of testing the net output, static navigation output, what is the output in this condition? That comes out as, you see, the net, net inertial acceleration will come. We said, okay, what is that? Here. this specific force, which is the measurable inertia force, and the gravitation vector, which is not measurable, when you add up these two, you get the real inertial acceleration, total inertial acceleration. So that being the premise, we will be coming back to this again in a short while. Here, the sensor, as the pendulum moves down in this red line direction, we say our output is just opposite, 180-degree opposite. This black line is supposed to be 180-degree opposite direction to this red line. The drawing is not good, but you please forgive me for that. And this I'm calling GI, and therefore the measurement by the accelerometer is, by convention, already I explained, it's in the opposite direction of this physical motion, and that is called minus GI. And to this, while being here, the measured acceleration, this is the measured acceleration now. If we add the gravitation acceleration, then I get the net inertial acceleration or the total inertial acceleration. So for that, let us take this measured vector, this one, this black line, and vector sum to the capital GI, which is the gravitation acceleration vector, and the vector sum of this and this will be pointing in this direction. The magnitude is same as this, but the negative sign will be removed. And this is the centripetal acceleration, as though while we are going around a circle of some radius r with certain angular velocity omega radians per second, at the case it is 15.02 degree per hour, then we will be traveling. This point actually is traveling, describing a circular motion in space, in inertial space, but we don't really feel that we are going like that. Actually, in 24 hours, we are really traveling through this circle once. And
excuse me, sir.
While we are in the...
Sir?
Is there any problem?
Sir, this centripetal acceleration will be towards the center of the earth or towards the center of the circle?
No. Center of this circle. This, I will come to that. This circle, you chip it. You chip the earth at this plane. Huh? You chip the earth like that, you get a circle. Okay. That circle. So that towards that center of the circle. Okay, not here. Okay, fine.
Yes, sir.
Yeah. So you have now the centripetal acceleration vector. This is what will be measured by the 3 accelerometers sitting on the launch vehicle, and then you do the integration. You compute your gravitation. All that algorithm will be run, and you really get what will be the position vector as we travel along this circle. Position, velocity, everything will come as though we are moving in this circle. That is the output that we are checking, and we call that static navigation. This is not a right word, but this is a good one person coined it initially like this, and maybe it's not a universal thing. It is coined in our in the place where I was working earlier. Now I am retired, so it is a specific name coined there. Okay, being static and being still navigating. So in that sense, this has come. So you see here, the vertical z-axis displacement is not zero. Is zero, and therefore there is no acceleration in this direction. There is no position, velocity in this direction, and they will remain the same. There will be only an initial z value that will be their position, but velocity and acceleration are not zero. And that is a check, in fact, whether our computation gives, our inertial navigation output gives any z component, and small z component will come, that is due to error, algorithmic error and other errors. But the ideal value is supposed to be 0 along this direction, but x and y will keep changing as you move along the circle. So what is shown here is simply the the gravity vector is the vector sum of the gravitation and the centrifugal, and the measured gravity vector is just opposite of this one, and the measured one plus the gravitation gives this positive omega square, or I mean you cannot say they are matrices. In this one-dimensional case you can say omega square r, and that is towards the center of this particular local circle, and this vector is what is integrated in the static condition, and it is the same thing. You cannot say when the vehicle moves only there is an acceleration towards this center. This is meaningless to say because there are acceleration in other direction also. So this is in the static condition only. So this is a very clear, interesting figure to explain what navigation algorithm is. When you exercise, what happens. This gives a lot of insight. For that purpose, I have taken this figure. Okay. Now, and this circle is same as what somebody asked now. Is this circle which is chipped at that at this height? I'm chipping the entire thing. I will get a circular outer ring kind of a thing inside that solid core. There will get a rib surface, and that is circular. And this circle is in the xy plane, and now this xy plane is shown, and their circle is shown here. And here now we are really going to move along this circle. The same for explanation purpose, it is redepicted. Now here, as we know earlier, we said, and this radius is capital R, that is this radius is capital R, not the Earth's radius. This is a capital R, and if you are at this particular point, then your position vector is R cos omega zt and R sin omega zt. And you can take the derivative, you get the velocity, and actually the velocity is going to change like this because of the earth rate. This omega z is earth rate, 15.02 degree per hour. And the second derivative, you get this, and you will find the vector direction you can calculate always. You see, the position vector is outward, and this acceleration vector is inward towards the center of the circle. So you can verify that easily. This is also to verify that I have put, so it is very simple, straightforward, therefore we will not spend much time here. Now, we are now ready to say navigation in inertial frame. Let me check the time. Yeah. Now, what we said, AMI is the measured inertial acceleration, and we are navigating in inertial frame, okay? Measured acceleration in inertial frame is equal to the total inertial acceleration except, remember, underline the word except, the gravitation acceleration. What does that sentence mean? That except is that from the total inertial acceleration, you have to remove, subtract that gravitation acceleration. Then this net will be nothing but the measured inertial acceleration. Now the same thing is rewritten in a different way here. This measured, who measures it? Accelerometer measures it. And what do we call that? Because measurable acceleration is called specific force. So therefore, people use the symbol F, specific force, measured by the accelerometer in the inertial frame. And that stands for the same symbol I put here, repetition. What is this total inertial acceleration? If I had a position vector Ri, then R double dot I is the total inertial acceleration. So it's straightforward. And this minus Gi is same as that. Okay. Now what we want is this fellow. Keep that there. Take the other one to one side, and you get the total inertial acceleration is equal to the measured inertial acceleration by the accelerometer represented by this symbol. A stands for accelerometer, I for in inertial frame, F for the specific force, so the measured. I told already the specific force is nothing but measurable inertial acceleration plus the gravitation vector, which is computed from a model. Add them up, you get the total inertial acceleration. Now, again, you look into this. In a vehicle, an accelerometer is mounted. It is impossible, it is very difficult to say that you should mount in the inertial direction initially. No. We will have some convenient, in the body we strap down the sensors, and therefore it will be, the accelerometers will be tied down to the vehicle body, that is in the strap down system it is so. So the accelerometer, which is measuring the specific force F, that is acceleration, is coordinatized in the body axis system. Body has got an X, body has XB, YB, ZB. Along those three directions, these three accelerometers will be there to measure the acceleration in that body axis directions. And that output measured is the body frame. This is the accelerometer output in the body frame measured by the accelerometer. In order to take it to inertial frame, we need to, because this is in the body frame, this need to be transformed to inertial frame by this transformation matrix C, body to inertial. And this term is nothing but this particular term. And of course, this is already in inertial, therefore we don't have to do anything. And you get the first navigation acceleration equation. R double dot I is equal to CBI FAB plus GI. And this is the first most important equation for navigation in the inertial frame. Now, I hope this is a very simple, inertial navigation is very simple. We don't have to bother about the other accelerations like Coriolis, centrifugal, Euler, nothing. So it's very simple in that sense. Now, we also studied this CBI. Suppose this is keep on, CBI is changing with time. That means there is a time derivative of CBI, and that we have already derived. It is the CBI into capital omega of the body rates in inertial, with respect to inertial expressed in body frame. This already we have derived. And using this, what we can say symbolically, CBI at any time is equal to initial CBI at time 0 plus this CBI dot, which is computable, and integrate and add, you get the CBI at any point of time, which is what is required here. Continuously varying measurement, and that is continuously transformed into inertial using this staff, and then continuously your position is changing, and continuously you calculate your gravitation vector at each point, add them up vectorially, and then you get the total inertial acceleration, and then you integrate. First integration gives velocity, second integration gives position. So in fact, that the navigation in inertial frame is, frankly speaking, is over. But just for the feel, to expand its field, I'll put in a block diagrammatic way. The gyroscopes are used to measure the angular rates, and they are also tied down to the body, and so their outputs come in the body axis. So what it gives is the body angular rates with respect to inertial axis expressed in the body frame is what is going to come from the gyros, and that you have to of course put in this form. That's what is done here, and then you get the CVI dot. From that, of course, you do some mechanization. This is not the way exactly it is done, but this is symbolic. So you get the CBI of T, and this is the accelerometer output, coordinatized in the body frame, and that is coming here. Using these two, you convert it into the measured acceleration in the inertial frame and put it like this, and then you take out the position, do the gravitation computation, get the gravitation vector, add them up, net vector you integrate, and this is what I exactly said in the previous slide. And of course you see here, because integration is involved, the initial value, initial position, initial velocity you have to input. Similarly here, initial value of CBI 0 need to be determined by called alignment methods and then inputted to the system. Once this and this are inputted to the system and the algorithm is running, you get the velocity and position in inertial frame, and that is what we want for the launch vehicle navigation to inject a spacecraft into orbit. Of course, you will also require either this Euler angles like theta psi pi or the quaternion which we have explained for the vehicle control purpose. That also is derivable out of this. So that is what is shown here. So we have this is of course okay. This is not required. This we have explained. So our inertial frame navigation is over. Okay. Now just I will go. This particular last class means not the disturbed class, even before that L5, lecture 5, we have derived this. Okay. So I request you to go through this equation which we have derived, and remember that, because it is very important to use this the moment we go for navigation in a non-inertial frame. For example, suppose I go for navigation in earth-centered, earth-fixed frame. Our frame is fixed to the earth, but earth is rotating, and therefore the frame itself is rotating. I repeat, if you want to do the navigation in earth-centered, earth-fixed frame, the axes are fixed to the earth, but earth is rotating, therefore the axes are rotating with it. Therefore, the navigation frame is rotating at the rate of that earth angular rate. So it is not an inertial frame, but the navigation still called inertial navigation. It is inertial navigation, it is called not because navigating in inertial frame or non-inertial frame. It is called inertial navigation because the sensors used are inertial sensors, and that is why it is called inertial navigation, not because of the coordinate system which you are going to use is inertial or not inertial. In many cases, aircraft, it is non-inertial frame. This ECEF is a non-inertial frame, but still what we are doing is inertial navigation only, and the algorithm will be different. So now we ended upon with a frame which is very popular frame in a global positioning system is using this particular frame. And this is the equation which I simply, the only thing is this two is combined here. In this equation, okay, it is written as 2 times it is written. That is the slide preparation, it happens so. Otherwise, it is the same equation which we have derived. I am borrowing it. Now, I make some simplifications. Here, the 2 frames considered was separated by a row. But here, we don't, because they are centered, the origin is the same. There is no separation. Therefore, the row is 0, row dot is 0, row double dot is 0. So therefore, this term is not there. And also, Earth rotates with a constant angular rate. There is no angular acceleration. Therefore, this omega dot is equal to 0. Therefore, this term goes and this goes. The remaining, you see, it is written here. So the equation gets simplified to this. Now, in this, this is R double dot I. R double dot I, just we will go back. We developed this R double dot I. Take this box. R double dot I is CBI, FAB, GI. You take this box. And put it here. R double dot I is CBI, FAB plus GI. It is same equation I am taking from ECI from navigation. Therefore, instead of this, I am replacing this here on the left hand side. That's all I am doing. All other things, no, nothing else is done. Now let's go to the next slide. Now, actually, I am interested in this R double dot N. So in order to get that, I am doing all these operations. So there is a CNI. So I multiply with IN so that this becomes identity. So this now I will be free to take it out. But I should do the CIN multiplication here and here also. And that's what has been done here. And when you write like that, these two can be combined. B to I to N is nothing but B to N. So CBN FAB. And gravitation in inertial frame is getting transformed to the N frame, some navigation frame. In this case, ECF, that we will give a specific symbol for that. Right now, we call it N. So this is nothing but now same gravitation vector, now expressed in N frame, that rotating frame. Okay. So this is here, and this become identity. You get the right hand simply what is there inside the bracket, and you retain this on one side and regroup it. You get CBN FAB, then you get a GN, and this term comes here, and there is a negative sign here, and this term comes here, a negative sign here. Then look at carefully. This GN, earlier it was GI omega I RI. That combination earlier was our gravity, small g, I call gravity vector. Now this is again gravity vector, but in N frame, that's all. So this is gravity vector. This is gravity vector in N frame. Now here I have used E. This small e I wanted to, because the N, I want to get rid of ECEF, I want to use that small e. The small e, when I look at it, I am more comfortable. Okay, ECF. That mental association can be easier. That's why wherever N is there, I simply replace with the small e. In this to this is that is the only difference. Now, this together as a vector sum is a gravity vector in ECEF frame. And this, as you know, is the Coriolis acceleration due to velocity rotating, due to a velocity on a rotating frame. Yes. And this is measured acceleration in ECEF frame. I think time is up. We need not hurry. And at this point, we can stop we have further interpretations which will take more time, these things. So at this point, we'll stop and take questions. Jenju, I think so far without any problem, it was presentation
Yes,
was
sir,
going on, I think.
Yes, sir, it was fine.
Yes, sir. See, I would say that static navigation, even though when explained looks very simple, many things are like that in engineering or physics. Once it is told, it looks simple. But visualizing that is not that simple. So you see a small that centripetal acceleration, which is the opposite sign of the centrifugal acceleration, when integrating gives the circular motion of a body sitting on the earth, going through in the inertial space, describing a circle, and this circle, uniform circular motion, all along in our school onwards, we used to study. You see how beautiful the concepts are coming again and again in real applications. Okay, anyone, anything you want to discuss? Professor Priyadarsanam, sir?
Sir, one discussion that that the accelerometer cannot measure gravity.
Gravitation.
Gravitation. Can you explain that in the physics point of view?
Yeah, you have listened that point, yes. Sir, in physics, you say that what happens when a body, accelerometer or body is in free fall. You say the gravitation is a conservative field. Gravitation field is a conservative field. The energy is conserved. The total potential energy and kinetic energy is always a constant. And so the accelerometer, forget about the pendulum sitting inside, what we have mechanized engineering point of view to have a deflection and sense it using some technique, electronic technique, that deflection, all that point, the engineering aspect. But pure science point of view looking at, there is no energy change coming on the total energy as it moves in a conservative field, the gravitation field, the total energy is not changing. According to physics, unless there is a change in energy, that is not measurable. So that is the one major interpretation that there should be a change in energy to measure something. The basic principle in physics. That's all, sir.
Two bodies, yes, sir. If two celestial bodies are there, they will be attracting each other. So this thing cannot be measured. That is the point.
Which is not measured, you are saying?
If two bodies are moving, two only in the universe, only two objects are there. They will be attracted to each other. So if I place an accelerometer on, is it related to that? No, I'm getting confused. You are saying that gravitation is a conservative field.
Yeah.
So in the conservative field, there is no additional energy difference.
There is no change in energy.
So only the change in energy is measurable.
If there is a change in energy, then only that becomes measurable. Measurability is possible. It is. Yes.
So then,
when we other one, I will tell you, sir. Suppose we are going to Mars. A spacecraft is moving towards Mars. Okay. Now, there also, it is not only Earth is involved, the gravitation due to sun, earth, moon, other planets, everything's gravitation field will come. We will have a net field. And there also the accelerometer output is zero. Because, yeah. Yes, sir. I think, what, anything else? The two body attracting each other, saying, that which part I am not getting.
No, I was imagining that accelerometer is one of the body and then Earth is another body. But
Okay.
however, Earth, when the accelerometer comes in contact with the Earth, then the acceleration in that opposite direction is measured.
Yeah, not contact with the earth. Okay, there again you have to be very precise. At the instant of contact, the total energy, the kinetic energy becomes zero, and the potential energy becomes some value. Or let's say that there is also zero as some reference value. Zero is not absolute zero, some minimum value, I call it zero. So there is an energy change. That energy change, where it goes, that energy goes, actually it comes, hits on the surface with certain velocity. That energy change will go as heat onto the surface of the earth. Now, once that is done and the body sits there, it is not able to freely move downward any further. It is constrained to move. That is the condition that we explained in the static condition. That is like feeling our weight while
So the
constrained.
condition makes the object to measure.
Measure, yes. Yes. Their energy change wise, you cannot say, okay, it is constrained. Okay, then the other statement I should add, the physics statement, I should add in an unconstrained motion, maybe because I am not a pure physicist, but an engineering man looking at physics. Okay, now I can work back. Okay, I should have added the word in an unconstrained free motion, if there is no energy change, like that, one may have to say. This I read somewhere, sir. That article I wanted to dig it out later. Some years back, I gone through an article. There was a beautiful article in which this was explained, and this is what I remember exactly. But later, I wanted to, even when I was there, I wanted to take this article and distribute to the students. I couldn't get it. But if you are getting anywhere, please give it to me also. But is there?
Sure,
Yes.
sir. Yes, sir.
Yes, sir. So, Deekshit, you are attending for the first time, I think.
Yes, sir. In between, I missed it. On the first day, I was there. Yeah.
So, how do you like it?
Yes, sir. So now onwards, I'll attend because in between few days, there was some other work to do. So.
Now I request you to listen the in-between lectures because we have developed the basics, and that is why in one slide we are able to complete our inertial navigation. Navigation in inertial plane, because so much groundwork we have done. That is why
Yes,
we are able to simply say that. So
yes,
without that, it's not possible. So we did so much of groundwork to make as simple as making it one slide. Ratnendra Singh, I think he has been attending
Yes,
earlier
sir.
also. Okay, Guhan is missing.
Gohan was there.
Pardon? Guhan is there?
He was there. He left a bit earlier today.
Okay. So, you, teacher, so you have any comments?
Yes, sir.
You can
Hello,
make
sir.
comments. You can make comments. You should.
Yes, sir. It was fine, sir.
Is it okay?
Sir, then it's okay, sir.
Okay. Then we'll.
Sir,
Priyadarshana sir,
can we wind
next
up the
class,
session?
we are going to take
Okay.
navigation in ECEF. next class.
Okay.
Yeah.
Okay.
So then you can wind up, Jinju.
Okay, sir. Okay. Sir, thank you, sir, for your presentation. We will continue the presentation on the next Saturday.
Okay.
Thank you all.
So thank you.
Thank you, sir.
Thank you. Thank you. Jinju, are recording off, eh?
Thank you, sir.
Thank you, sir.